Well, hi everybody. My apologies in advance for the dishwasher noise in the background, but I have a bad habit of not turning it back on after I make these videos, so uh, hopefully the noise won't be too much. Just quickly, I'll try to go fast through this video, but so you can pause and look at it as needed. But first of all, end of last lecture, I switched the we noticed right after class that you got to the ninth power, and the simple solution is that I meant to put the cube atlas in the domain and the standard atlas in the codomain, or in the range, if you will, of the epsilon map. And if you do that, then that makes it a genuine diffeomorphism of Rn with the cube smooth structure versus Rn with the standard smooth structure. So they are in fact diffeomorphic, and we were we were really close to it. I mean, if I could just read Jeffrey Lee's book as it's plainly written, then we'd be fine. But so that's that. All right, so let's move on here. So I have a number of calculations to share with you guys, basically just to support your homework and to just try to demystify the examples in Jeffrey Lee's book, which I don't think are terribly unclear. It's just, sometimes we don't know where to get started. So let me just basically just work through some stuff and write some stuff down. So first of all, what's the charts on the N sphere? So this is the stereographic charts. Yeah, okay. I had some preliminary calculations I did for the two sphere. I guess those didn't make the cut. That's fine. In practice, I think it's, if you're stuck, work out the two sphere and then go from there, or work out the circle and go from there. But anyway, so these are given. Basically delete the North Pole or delete the South Pole charts. Chart domains. Of course, the union of those two gives you the whole N sphere. And here's characterization of what they are. And here's the definition of stereographic projection in this context for the N sphere. You divide by 1 over 1 minus x to the n plus 1, or 1 over 1 plus x to the n plus 1, and multiply by the points, the point x1 through xn. These are given, of course, in the textbook, but what's not given is the inverse function to these, right? Now, we did find it's on page 30 of the other Lee textbook, right? But I think it's helpful to see the derivation, so let's look at that. All right, so to find the inverse function for a given function, what I do is I put y1 through yn equal to the output of the function, and then to find the formula for the inverse, I simply need to solve for the x's. My goal is to solve for the x's. So I go about that business. First of all, I notice that y sub j is equal to x sub j divided by x divided by 1 minus x to the n plus 1. It's not x to the n plus 1, it's x sub n plus 1. And so you'll notice this, guys, is like these books and myself, we can't make up our mind whether or not we're going to subscript or superscript variables. And my apologies, like, something that should be fixed in a final edit of a book or something, right? But, okay, anyway. So this gives me the equation that x sub j is equal to y sub j times 1 minus x to the n plus 1. Of course, these are x's from a sphere, so we also know that the sum of the squares is equal to 1. That defines the n sphere in terms of its equation. And let's see here. So then, like, after some algebra, you can prove that the inverse map is in fact this and that, respectively, for the south and the north charts. These are the inverses to the south and the north chart. Now, these formulas are by no means obvious. Let me show you why they're true. All right? So here's the derivation. All right, so going back to the equations I just found, I'll box it and call it star. So I know that x1 square, the sum of the squares up to the n minus 1, up to the n plus 1th one, is equal to 1 minus the square of the n plus 1th one, right? But the difference of squares gives me the product here, like so. But then I can, of course, plug in the star equation into this, and I've got like y1 times that squared, yn times that squared. Like, you know, I just basically plug these in to do all the way across. And then I can factor out the y1, the sum of the squares of y. That's exactly the length of the n vector y, times 1 minus x to the n plus 1 squared, right? And then, of course, that factors like so. Excuse me, this is still equal to that, and then, so I've got this, and then I can divide by 1 minus x sub n plus 1, because that's not equal to 1, so I'm not dividing by 0 in this context. And lo and behold, I get 1 minus x to the n x sub n plus 1 times the length of y squared is equal to 1 plus x sub n plus 1. And then, what do? Well, then I solve for xn plus 1, and then that's, okay, well, that's half the battle. Okay, it's not really half the battle, but it's a certain percentage of the battle depending on what n we're looking at. But anyway, there's the last component function for the inverse. There it is. And then once you know that, then you can take that and you can basically go back up to the star equation. I think, which one did I go back to? What did I go back to? Once I know that, I'm trying to remember where I go back to. From star. Okay, so that's xn plus 1. Alright, and then I did, oh, I know what I'm doing. So in the equation for star, up here, I have a 1 minus x sub n plus 1. So basically I want to find a formula for that factor in terms of just y, and once I do that, I can plug it in there and that'll give me the formula I'm looking for. So I found this star equation, right? And then from that I can figure out what 1 minus x sub n plus 1 is. So I do that, I get this, and then when I plug that into star up here, right, plug it into star down there, I get that formula, and there it is, lo and behold. You know, the inverse to the South Pole chart is as follows. So there you go, that's the inverse to the coordinate chart which is given. And let's see here, what else do I do? So I'm like, I think we're getting, I don't know if this is exercise 140 or I'm just trying to lead you to exercise 140. It doesn't really matter. These calculations are helpful for the discussion around exercise 140, okay? It might even be a solution to exercise 140. You need to think through that, all right? I'm gonna try to give you some bones, but you need to put flesh on the bones still, right? Oh man. Just a second, I gotta go grab my my whiteout. All right, I'm back. So apparently I decided that I was going to relocate this equation down below, and so I did, and so let me get rid of this hanging non-equation. There we go. Fixed. Cool. Now, so that's the North Pole, that's the South Pole, and if we look at the image of the North Pole under the North chart, we get 0. The image of the South Pole under the South chart, we get 0. So the poles map to 0 if they're in the domain of the chart. And and then this, let's see, what am I doing? Now I'm just checking my work, making sure that actually it was a genuine inverse, so I'm just composing it. And look, it works, yay. And among other things, that shows me that the South map, the South chart, is in fact it's surjective onto Rn, right? So if it's surjective, it's a bijective map. It's onto Rn. We know that the North Pole maps to, the South Pole maps to 0. Then if you delete the South Pole from this domain, what are you mapping to? You're mapping to Rn without 0, right? And similar comment goes for the North Pole map. And so if we take the intersection of the North and the South charts, I guess that gets us to Virginia, but it's debatable. Anyway, let's see here. So the intersection of the north and the south chart, basically that's the sphere modulo the poles. And so if we look at the north chart or the south chart and where it sends this intersection, it sends it to Rn, you know, with 0 removed. All right, that's what goes on. So that's just kind of some bookkeeping there, seeing how the north and the south charts on the sphere and sphere work. There it is. Now let's look at the transition functions. Here are the transition functions between the north and the south, or the south and the north, depending on how you want to read that. Fine, whatever. And so here is my formula for the inverse function we derived, and then I need to feed that guy to the south chart, which remember is 1 over 1 minus the last component. And the last component here is this divided by that, so that's why that's there. And this is just literally whatever the components are inputted, like the south chart just takes what's in it and it puts it back again for the first n, ignoring the last one, right? So that's what's going on here. Just the first n of them repeated, and of course that fraction, I can pull the scalar multiple of 1 plus the length of y squared out, just the same in the map. If you don't see this immediately, just work it out for yourself. It's not that complicated, this part, all right? It's not that complicated. And then you multiply this through, and stuff cancels, and you're just left with a 2y squared, which is lovely because then that gives us 2's cancel, and we get y over the length of y squared, which is what we're told to find in the textbook, right? And like so, for slightly different reasons, but very similar calculational reasons, the transition functions the other way around is also y over y, length of y squared. And since the context of the transition functions is Rn with 0 removed, we see that we've got a smooth transition function because the only trouble spot for this in terms of differentiability is 0, and that's not encountered in the context. Therefore, we have an atlas because we have a pair of compatible charts whose union of domains covers everything. And in this case, the n sphere just has 2 charts. It was a little bit troublesome to calculate the transition functions, I would point out. In contrast, the projection atlas, which is something like this, phi plus minus x, blah, 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 has much easier algebra, but a proliferation of charts. Now, I was going to write up some notes on that, but I see I didn't, and my apologies, I'm out of time. But I think you guys can do this part. And here I'm just talking about, like I was doing for the circle. Well, if we can, with like just basically projecting onto the Cartesian axis for, just dropping one of the coordinates on the n sphere and keeping the rest of them, that defines a chart, right? And the inverse to that chart is simply obtained by basically mostly an identity map, plus either plus or minus like the square root. And the square root is, how to specifically find it, you have to go through the equation of the n sphere, right? So it's, you gotta think through it, but the I would call these the projection atlas. It's much easier to understand how to construct the chart and also how to find the inverse to the chart, sure. But the downside is then you have not just 2 charts in your atlas, but you have many. Even for the circle, we needed 4, I think, right? The north, the south, the east, the west. So yeah. On the other hand, understand the beauty of the stereographic projection, 2 charts for an n sphere. By the way, the number of projection charts increases with increasing dimension because you gotta think about, you've got a plus and a minus for each one. I think there would be 2n charts if I'm not wrong. Let me see if that makes sense. Maybe 2n plus 1 actually. Maybe 2n. The circle is just the 1 sphere. We needed 4 charts. So it may be 2 times n plus 1. That's the number of charts for the projection atlas, but I haven't worked through it carefully, so I could be counting wrong. Don't count on me. anyway, that would be a good addition to these notes, is like the working out the projection atlas, but maybe that'll come up in my solution for the homework when I finish it. I'm just trying to get you guys like well, I wouldn't say this is more than a hint. This is more than a hint. All right, so projective spaces is the next topic, and I start by just taking a few pages to look at the case of RP2, the real projective plane. The real projective plane is essentially the set of all lines in R3 through the origin. And so as we read these notes, we'll see a progression of notation. Eventually I'll come to terms with the best notation, all right? But to start with, I'm just suffering through the kind of notation that Jeffrey Lee gives us to start with, which is not really very helpful for calculational purposes. And that's intentional. He wants the reader to figure it out for themselves. That's kind of the point. Now, let's see here. So like these are the three different charts for RP2. Either you've got lines which are not parallel to the XY axis, not parallel to the YZ axis, or not parallel to the XZ axis. Another way of saying that is we've got lines which either pierce the plane z equals to 1, they pierce the plane y equals to 1, they pierce the plane x equals to 1. Right? Every line that goes through the origin, and my lines should go through the origin, guys. My picture ain't right. This is not, it's not right. Like, my lines are supposed to go through the origin. Oopsie. But I just made the lines, I thought they would look cooler like that, and I was, well, anyway, I have no excuse. My apologies. The lines are supposed to go through the origin. All right, fine. Enough said. But anyway, so like, what's the formula for this assignment? So the chart in each one of these cases is to assign to that line that point, assign to that line that point, assign to that line that point. Now, it's not exactly that point. It's throwing away the x, throwing away the y, throwing away the z, and just keeping the xy, keeping the xz, or keeping the yz in this context. So here are the charts. Phi z of L is the x of L, the y of L, that point. Phi y of L is the x of L, z of L, it's that point, except ignoring the y. And, you know, here, except ignoring the x, all right? And so he, you know, I think Lee gives the description. Okay, so like phi z of L is u1, u2, where u1, u2, 1 is an element of the line. Or phi y of L is u1 and u3, where u1, 1, u3 is an element of the line. And like phi x of L is u2, u3, where 1, u2, u3 is an element of the line through the origin. And I mean, fine, you can do that, but it doesn't really, kind of like, you know, fine, but how do I calculate a transition function from that, you know? We really need formulas. And, well, I need formulas. Maybe other people don't, but I need formulas. All right, so here we go. So what does this mean? Phi z of L is x of L. What does that mean formula-wise? Well, let's look at it. What is the line through the origin? It is the scalar multiple of some vector ABC, right? And if this is in the UZ chart, that means it can't have C equal to 0. C has to be non-equal to 0. In other words, the line is really the span of that point, all right? And so we're going to start using bracket ABC for the notation of the span. In fact, we'll soon even drop the parentheses here and just write brackets ABC. All right, anyway. So we've got this point, x, y, z in L, with z equal to 1. In order to get that, in order to get z equals to 1 in the line in question, we need ct to be equal to 1, which means t is 1 over c, which then means that x is ta, which is a over c, and y is tb, which is b over c. Therefore, the formula for the z chart of the RP2, the real projective plane, is simply the quotient of a divided by c and b divided by c. And in this context, we're assuming c is not equal to 0, so these formulas make sense. Of course, there's also an ambiguity which must be dealt with here. The ambiguity is this: the description of the line as being generated by a vector, it suffers the rescaling problem, right? And so this is essentially the theorem we have to deal with. Any multiple of ABC generates the same line if lambda is a real number. All right, so like, that's both a blessing and a curse. It's a curse because we have to think about it. It's a blessing because it makes the formulas beautiful. But you see what happens here is if I choose a different representative by multiplying by lambda, I get a multiplication by lambda of A and a multiplication by lambda of C, and so they cancel, and we're still left with the same output. So despite the fact that there is a degeneracy in terms of the representation of each line, in terms of picking different generating vectors, it matters not, because this formula is single valued nonetheless, because the rescaling doesn't change the output. It's a well-defined map, in short. And the formulas for the phi x and phi y are similarly derived to be division by A or division by B of the other variables involved. So there you go. Those are the charts that those are the formulas for like that's the formula for these points. Boop, boop, boop. That's the formulas. If we express L as like, it's like this L is literally A, B, C, and that point right there, we can get that point to be specifically, it is A over C, B over C, and 1. That's the point of intersection. That specifically is the point of intersection after we do the analysis. All right, assuming that L is generated by ABC, and in this context, C can't be 0. If C was 0, that would mean the line is parallel to the plane and we'd have no intersection. All right. I hope that helps clear things up a bit. Now, so once I have formulas for the charts, like actual honest-to-goodness formulas, then everything starts to fall into place pretty easy. First of all, I can just write down the formulas for the inverse. I didn't need to derive them here. I could just see it. Like phi z inverse, we just keep the x and the y and tack a 1 onto it, tack a 1 in the middle of it, tack a 1 at the start of it, and this will give me the line generated, which gives me back these points. And so, like, here's the proof that the inverse formulas that I pulled out of the thin air work. Again, you could derive them, but I'll let you do that. I don't feel like it at the moment. So phi z composed of phi z inverse of this is that, by definition, by my claim of that being the inverse. But then when I let the phi z chart do its thing, I get u1 over 1 and then u2 over 1, which is u1, u2, which is what I want, right? And likewise, if we compose the other way, if I feed it the line generated by ABC with C assumed to be non-zero, then by construction, phi z is A over C, B over C, like so. And then the inverse map says you just put this there, you put that there, you tack a 1 on it. And then the thing is we use the theorem. See, if we get this, well, that's equal to that, because I can just multiply this by C and I have the same line, right? We can choose a direction vector for the line by rescaling the direction vector if we so desire. So there you go. There's proof positive that we have 3 charts for the real projective plane, and in fact they have inverses. We have formulas for them. So what's left? Well, let's show that the transition functions are smooth, yeah, for the real projective plane. So here's that. So the transition functions for RP2, like so. I've got this one, I got that one, and I calculate the composition. I get these lovely formulas. In this context, we're looking at the place where both u and the v are non-zero here, I believe. I'm not being super careful about the domain, so maybe you should think through that. All right, but here's the formulas anyway, and as you can see, the uv mapping to these or these in the context that u and v are both non-zero, which I believe is our context in this intersection here. Those are smooth transition functions. And of course, I could belabor this point further. I could look at the other transition functions like x to y and also y to z, right? I think there's, I want to say there's 6 transition functions in total to think about. But the calculations will be similar to this. They're all smooth. All right, so I'm going to move on to RPN, real projective n space. All right. So yeah. The great thing is though, now guys, if we ever have these examples again, we have an atlas that we can use, and if I give you guys a function from one of these spaces to another, then you've got the charts. So you can check the smoothness by checking the local coordinate representatives on the atlas that we've found, and hooray. Anyway, so the real projective space is all lines through 0 in Rn plus 1. So Jeffrey Lee talks about, you can talk about the pi map from non-zero n plus 1 vectors to RPN, which is simply the pi map. Pi of x is the line which x generates, right? In other words, map x to the span of x. And now this, of course, is not unique in the sense that, like, it's not injective, I should say, because any non-zero point in here which lies on the same, any 2 points which are scalar multiples of one another are going to map to the same line in real projective space. Here it is in a nutshell. The line generated by x is the same as the line generated by lambda x for lambda not equal to 0. The choice of x here is, of course, not unique. And, this is getting ahead of the game for you guys because you're just taking topology, although this should be old news for Ernesto. The subset of real projective space is open if and only if the inverse image under the pi map is open. In other words, we give RPN the so-called quotient topology generated by the pi map. In so doing, this makes the pi a continuous map. So that's the topology in here. All right, but again, we're going light on the topology, so I'll stop talking about it. Here's the charts for a real projective n space. We simply look at all the lines where the ith one is non-zero. So we insist that the direction vector for the line not have a 0 entry at the ith position. All such lines collectively form the chart UI, and we do that for each I ranging from 1 to n plus 1. That gives us n plus 1 charts for real n projective n space. Those are the chart domains. What are the formulas for the chart? Well, if you think about it, he says it's how's he define the map? He's like, man, did I write it down? I might not have written it down, but he's basically like, so you just, where at? Oh, I guess I didn't write it down. But I don't think this formula is in Lee. I might have thought, I don't want to, I'm going to be lazy and sit here, but some of these formulas are not in Lee. I just extrapolated from what I've already done in the, RP2. But here it is. I mean, this has to be the formula because if you look at the line generated by A1 through AN plus 1, and that's specifically, scalar multiples of A by T, if we put xi equals to 0, right, then that would give us t a to the I equals to 0. And that means that we must have a sub I not equal to 0 so that x sub I is not identically 0. So if a sub I was equal to 0, then we'd be in trouble because the line would actually lie in the the ith coordinate equal to 0 hyperplane, which is where we're not supposed to be. So in short, that means that a sub I is not equal to 0, or a upper I is not equal to 0, which means by the rescaling lemma, we can just make it equal to 1. But once you know that, then if you want to define the mapping, the chart mapping, we're just going to divide by x sub I, which we can do because x upper I rather is non-zero. So that's the chart that we're going to define. I guess I don't have to motivate why that's the definition. I mean, that's my claim, is that defines the chart. And in some sense, I guess Jeffrey Lee is defining the chart by its inverse in some regard. He's kind of cagey the way he describes it. He doesn't give you this formula, I don't think. I think he wants you to discover it for yourself, which is good. It's good. But the inverse to this is that. And you can run through the composition of these two and see that it in fact works out, all right? Maybe I did that. No, I didn't do it. I said, all right, well, that's good. Starting to get bored with real projective space, to be honest. I hope I've given you enough, though, that you can, really do a solid job on the homework with what I'm giving you here. Now, so the transition functions, then, the composite of, the ith and the jth inverse chart on real projective space, that calculation looks something like this. So here's my formula for the inverse. I put a 1 in the jth spot, and then we take the quotient of the coordinates here, all the coordinates except for the ith coordinate, by the ith coordinate. And I don't know where the ith coordinate is in here. I'm assuming that I is not equal to j, of course. I might be assuming like I is less than j or something. I don't think the notation necessarily says that. I don't see it. I think it's pretty okay. But definitely we get division by u sub I in this, and going the other way we get division by u sub j. But in this context, the place where we can study the transition functions, it would be in the intersection of the chart domains, which would be where both u sub I mean u upper I and u upper j are both non-zero. So these would be, of course, smooth functions. U assigned to that is a smooth function. U assigned to that is again a smooth function from Rn to Rn. I think it's one of the things I think is kind of interesting is if you think about the intersection of all the chart domains, it's a thing. Like they're not, I draw pictures sometimes like there's not a common intersection between all the charts, but for real projective space, at least as we're defining the charts right now, every last one of these things intersects because of the nature of the chart domain. I don't know. Real projective space, I think, it's a useful example because it forces us to be a little bit abstract, right? I mean, I don't know. Maybe you can visualize it. I don't have a visualization for you. Maybe we'll find one as we go on here. Maybe it's already just staring at me, and if I could just, really appreciate what's said right here. Since, the intersection of the line, the real projective space point, which is a line, and the end sphere is just a pair of antipodal points, we can use the end sphere to model RPN if we simply identify the antipodal points on the end sphere. In other words, the end sphere modulo the antipodal equivalence is diffeomorphic to RPN. So, that's interesting. So in some sense, real projective space is kind of like a sphere that's kind of got its different sides glued together. That's, man, what is that? Well, it is what it is. All right, anyway. So the notation, which I've sort of already been using, but Jeff really also introduces sort of at the end of everything, is the homogeneous coordinate notation, which is simply that for an n+1 vector, we're going to say it generates that line in RPN, and just use, so that is, basically, it's the same thing I was just talking about. It's the span of the vector x1 through xn+1. But we're just dropping this, anyway, just shorthand for the span of this vector, all scalar multiples of it. And of course, it's called homogeneous. Homogeneous refers to this fact that we can factor lambda. We can multiply by lambda and not change it. That's the homogeneity that's being mentioned. And here's his chart. In the homogeneous coordinates, he's like, here's the formula for the chart. So he does have the formula for it eventually. Just it's kind of on the page after where you're kind of looking for it. But anyway, he's got a 1 hat here, but here's how I write the formula. Whatever, it's all good. So that brings us to complex projective space. So if you've done all this, then complex projective space should be pretty relatively straightforward. Don't ask me to visualize it, but I can give you some formulas. One thing at a time. All right, so, oh man, What is that? Huh. Funky. Got like little whiteout stuff. All right, so see, complex projective space is the set of all one-dimensional complex subspaces of n plus 1 complex space. Well, a complex subspace, a one-dimensional complex subspace, is a two real-dimensional subspace. So in some sense, this is like, of course, here this is really our 2n plus 2. All right, so it's something like planes. The points in this thing are in some sense like planes through the origin in our 2n plus 2. Isn't that weird? So this should have something to do with that other example, which is mentioned in both of the books, right? Both of the books by Lee the Grassmannian. And that's a more formidable example, but it's a natural extension of what we're doing, all right? And hopefully we'll get back to that eventually. Okay, anyway, so let's focus on where we are. So the complex, basically play the same game with the complex projective spaces that we've already played. The charts are just going to be like lines that, the lines which are not contained in the complex hyperplane zi equal to 0. So like you could write L as the span of the n plus 1 vector of, this is an n plus 1 complex vector. In other words, it's the C span of Z, where I'm writing Z for that as a vector. It's equal to this as well, right? And so you could basically these you could use Z1 through Zn plus 1 as quote unquote homogeneous coordinates for L, where this time we get to multiply by a complex scalar. Yay. The coordinate chart is the ith coordinate chart. We're just going to divide by Z sub I just like before, and you can check that that is in fact an inverse. Excuse me, we haven't got to the inverse yet, but you can probably guess what the inverse is to this map, right? Like you won't be surprised probably if I were to tell you that the inverse map is. Actually, do I even write it down? I guess I don't. I think at this point I just start talking about CP1. But you could probably guess what the inverse map is to this, right? What would phi of let me just call this thing. Let me use a different letter just for the sake of. I'll use U's, but I don't know what to use. Fine, I'll use. Whatever. How many do I got? Well, there's one missing here, right? So like U1, U2, UN. All right. And I'm talking about the inverse chart, so it's supposed to go from, this is of course an element of Cn, right? And we want this to give us back an element of complex projective n space. So what do? We generate the line with homogeneous coordinates u1 and u2 and u I minus 1, and you put a 1 there, and then you keep going with what you already had there. And oh, my bad. I see the difficulty. Well, maybe that's okay. I'm trying to think. I think it's. Let me put some quotes on this. I'm relatively sure that that's what it is, but I got to think about some things. I think that's it. At least it makes sense. That's an n plus 1. I do believe that would be an element of, an element of UI, which is what we'd like, right? Which is a subset of complex projective n space. I think everything involved here works pretty much the same as the real projective space. It's just now we're talking about a tuple of complex numbers as opposed to real numbers. But it's pretty much the same song and dance. right, so I'm going to follow Jeffrey Lee here and talk about CP1 for a bit. All right, because he has some explicit formulas he'd like for us to derive, and this is to put us in possession of a specific correspondence that's a low-dimensional accident, I guess. But it's an important thing to know about. So anyway, here, there's a typo, by the way, in exercise 1.46. He's just got U1 intersect U2, but that's almost certainly supposed to be phi1 of U1 intersect U2, which is equal to phi2 of U1 intersect U2, which is complex modulo 0, complex with 0 removed. Remember, CP1 is lines in C2 which go through the origin. And so there's two different charts to think about, the one U1 and U2, U1 being the lines which are generated by a complex 2 vector with the first component non-zero, and U2 the lines generated by a complex 2 vector with the second complex entry non-zero. Of course, you can view these as vectors in 4 dimensions, 4 real dimensions if you want, but we'll keep a complex notation because it's like way easier and more to the point. So here's my coordinate chart, phi1. Here's my coordinate chart, phi2. It's the ratio of z2 to z1 or z1 to z2, and those are both defined. And they're both defined. I don't really need parentheses here, do I? It's just a single quotient of complex numbers. I don't really need the parentheses there, fine. But all right, so phi1 has z1 not equal to 0, phi2 has z2 not equal to 0, so these quotients make sense. And here's the formula for the inverse, which is unsurprising at this point, I hope. Of course, you can check me on it. And so if you look at this, then the image of the intersection, it's going to be where z1 and z2 are both not 0. No. Let's see here. So the only thing you can't get in this image is 0 for the output, because 0 puts z1 and z2 both equal to 0, which we cannot have. We can have z1 equal to 0 for this one. We can have z2 equal to 0 for that one, but we can't have both z1 and z2 equal to 0 if we're talking about both charts working at once. So we're asked to prove that the, I think we're asked to prove, but here's the calculation. It's kind of dumb. The transition function of phi2 with phi1 inverse, I put a script z in there. I don't want you to think that that's a complex vector. It's just one complex number, okay? So like I've used z as like a complex 2 vector up here, so I was trying not to like also use it as a scalar, but I probably have failed in that regard somewhere here. But that's why I made a funny looking z and then used a w here. But whatever. Just announce the type of variable you're using when you write the equation, then it won't be an issue. But this is for z, a complex number, a non-zero complex number. So the inverse maps me to 1z, and then phi2 says you take the quotient of this by that, which gives you 1 over z. Now this one says you put w1, and then v1 says you take the quotient of that by that, which gives you 1 over w. So the transition functions for this atlas are indeed what they should be. They're a smooth assignment of z to 1 over z or w to 1 over w. And then he goes on and he says, well, you could also do conjugate charts, right? If you want another nice chart for nice formulas, the conjugate chart's a good thing to look at. So it's defined in the natural way. And so like here's the formula. The phi1 conjugate is actually the quotient of the second coordinate conjugate divided by the first coordinate conjugate. And likewise, the inverse would be defined like so. So when you look at the transition function of this and that, you get phi2 of 1 comma z conjugate, which then by the definition of phi2 is 1 over z conjugate. There you go. So it wasn't too bad. And now there's a typo here in this part of Lee. He's got phi1 composed of phi2 inverse, but almost certainly that's supposed to be phi1 conjugate composed of phi2 inverse of z. So with that adjustment, we get this is equal to that is the conjugate of 1 over z, which is 1 over z conjugate, which is z over z conjugate, which is, in terms of the real underlying real variables, x plus I y over x squared plus y squared. And at this point, he's like, wait a minute, we've seen that before. That's the transition function for the sphere, for the 2 sphere, right? Because you remember we had y over y squared, but for S2 inside S3, that would look like y1 comma y2 over the length of y1 squared plus y2 squared. So just understanding that this is just the same formula in different notation. Wait a minute, so that means S2 is diffeomorphic to complex projective 1 space apparently. Okay, well that's the claim, inspired by this the similarity of the transition functions. See, because in some sense, guys, and maybe I haven't made this clear yet or not, but if you have 2 different spaces that have the same transition functions, it maybe indicates that they might be diffeomorphic spaces. There's probably a theorem you could prove there. Now, transition functions are local data, and for diffeomorphism, we also need a global bijection. So you gotta go up against that. There's some discussion of local diffeomorphism. Local diffeomorphism meaning that if you can find a function from some subset of a manifold to another, which is a diffeomorphism in that restriction. Every global diffeomorphism is a local diffeomorphism, but the converse is not true because of the usual issues for bijections globally. But all right, so here's the he uses like a z and a w. I just used f1 and f2. So I'm defining f1 to be this, f2 to be that, and the claim is that this f gives you a diffeomorphism from the sphere. X is an element of this 2 sphere, and here's the corresponding elements of complex projective 1 space. Now, this is an interesting formula because it's not like these are distinct cases. There's in fact a lot of overlap. So it begs the question of being well defined. Here's the proof that it is. I haven't done all of exercise 1.47 here. I've just done some of the legwork for it, which is also in Lee. So why is f of x well defined? If we could have x3 not equal to 1 and x3 not equal to minus 1, right? Now notice that 1 minus x3 squared is equal to x1 squared plus x2 squared, because of course the sum of the squares has to be 1 since x is a point in the 2 sphere. And in the context of the overlap of these cases, right, which is when you have x3 between minus 1 and 1 not inclusive, well then we can study what is the f1 of x and f2 of x, how do they behave together. Well, notice that their product is this, which simplifies to 1 in view of the equations on this page. And as such, that means that the complex projective the line in CP1 represented by f1 of x1 is the same as the line represented by 1 comma f2 of x, because the product of f1 and f2 is 1. So that shows you that in fact this formula, despite its appearance of not being perhaps well defined, it actually is well defined, and as such is a function. And as it being a function, then we can test for it being a smooth function. And to do that, we just have to, show that to show it's a diffeomorphism, we need to check that it is in fact a diffeomorphism. In other words, it is a one-to-one, an onto function from the 2 sphere to the CP1, and also that if we look at the local coordinate representatives of it, with respect to I don't know for sure this is the right choice. I can't remember. I didn't read these super carefully. I have a suspicion that he wants you to look at the conjugate atlas. That might make for nicer formulas. But listen, you could do phi1 and phi2 here. You don't have to use the conjugate one. It shouldn't really matter. if you can prove that the local coordinate representatives are smooth with respect to a choice of atlas, then you got it, right, by our theorem. Because if we have smoothness with respect to one choice, one local coordinate representative, any other compatible set of charts that we can re-represent, the function will necessarily be smooth because the given local coordinate representative will be the composite of transition functions, and the representative you've already got is smooth. Anyway, we went through that last time. Jeff helped me, remember? And anyway, so like here's what comes to mind for me. These are the transition functions we should technically check. My suspicion is once you check a couple of them, it'll be like, okay, well, I know what's going on here, and you know, once you do one, the others will be faster. But anyway, you should see that these are smooth, and once you do that, voila, you've proved that, you know, F is the sphere is diffeomorphic to complex projective one space. But again, I do think we also need to check on F being a bijection. But that's not manifold theory so much as it is just like essentially pre-calculus, but pre-calculus with more letters. Anyway, I hope this helps you guys. Past this point, there's a few exercises I assigned, but those should all fall into place now. Once you've done these exercises, then you have in your clutches the atlas for each one of these examples. So the problem of showing that those maps are diffeomorphism, I'm hopeful should be relatively straightforward given this context. So anyway, the only other significant example which, you know, kind of remains for us in the chapter 1 is the Grassmannian, which I don't want to do at the moment. I don't want to, I think that would be like a little bit much for us at the moment. In John Lee's book, there's some nice examples of smooth maps, but I might go over those in class next week. I'm not sure. I'm more likely just going to go on the tangent structures because I think we've got a good base of examples under us, and I think we should be able to go on. And so, anyway, I think with all this, you guys should be able to get through the homework without it being, you know, too horrible. And I will still help you if you come ask me questions. It's all good. Anyway, have a good weekend, you guys. Thanks.